Welcome back to the Deep Dive. Our mission, as always, is to take complex tech, break it down, and give you the core insights.
Yep, straight to the point.
Today, we're heading into the cloud. Specifically, we're going to dissect the architecture of Snowflake.
Right, it's a big one, a platform that's really reshaped the data landscape.
It definitely has. And we want to understand why. What's under the hood?
It's more than just, another data warehouse. It's really a fundamental rethink of how compute and storage should work together, especially in the cloud era.
Exactly. So we're not just scratching the surface with marketing terms today.
No, we're going deep. We need to unpack the technical details, you could call it the secret sauce that makes Snowflake perform the way it does.
We're focusing on the core structure, the three key architectural layers. If you really want to grasp why Snowflake's been so disruptive, understanding these layers is, well, essential.
Absolutely. And, to really get it, you have to think about where we came from. The older system.
The legacy data warehouses.
Exactly. Traditional data warehousing, it was often monolithic, tightly coupled systems.
Built for a different world, really. On-premise.
Right. And they really struggled with two massive challenges that define data today. Just the sheer volume of data and handling lots of different users and queries at the same time. High concurrency.
Okay, let's unpack that a bit more. Snowflake is often called the definitive data warehouse built for the cloud. Why that specific phrasing?
Well, because it didn't just try to lift and shift old ideas. It looked at those limitations you mentioned, the resource contention, the inflexibility in scaling, and saw them as fundamental flaws.
Flaws to be fixed, not just managed.
Precisely. They needed a completely new architectural approach. And the absolute cornerstone of that approach is separation. Total separation.
Okay, separation. Let's dive into that. That seems like the place to start.
It really is the foundational shift. To understand why Snowflake works, you first have to appreciate what didn't work so well before.
Those legacy systems we mentioned.
Yeah. Think about how they were built. You often had, a big appliance box or maybe a carefully tuned rack of servers.
Right.
But the key thing was the storage where the data lived and the processing power were locked together. Physically, logically, financially.
Like a package deal you couldn't unbundle.
Exactly. If you needed more storage, you often had to buy more compute with it, even if you didn't need it, or vice versa. It was inefficient, and you paid for that inefficiency.
And that led to problems, right? Like resource contention.
Oh, absolutely. That was the nightmare for database admins, for DBAs. Picture this. Big company, okay? They're running a huge ETL job overnight, extract, transform, load, takes hours, hammers the system.
Standard procedure for many places.
Right. But then maybe the sales team needs to run some urgent queries for their morning meeting dashboards. They hit the same system.
Boom.
Pretty much. Collision. The big ETL job is hogging all the disk I/O, chewing up CPU. Suddenly, the sales dashboards are slow, queries time out.
Not good. Performance tanks. And it's not just annoying, right? It impacts the business. Yeah. SLAs get missed.
Totally. And the data teams end up spending their time fighting these internal infrastructure fires instead of actually, delivering insights from the data.
And scaling was another headache.
A massive one. Scaling was slow, disruptive, and incredibly expensive. Let's say your beta volume doubles, maybe an acquisition, maybe just organic growth.
Okay.
You couldn't just add more storage easily. You typically had to upgrade the entire system. That meant long procurement cycles, planning for downtime, major capital expense.
And you had to buy for the future peak, right? Not for today's needs.
Exactly. You had to over-provision massively. You'd buy this huge, expensive system designed to handle the busiest hour of the busiest day, maybe Black Friday and the rest of the year. A huge chunk of that expensive hardware was just sitting there idle. Burning power, costing money.
So Snowflake saw this and thought, there has to be a better way.
Precisely. And their core innovation, the absolute game changer, was this principle, completely separating the database storage layer from the query processing layer, a clean break.
Why was that possible now? The cloud.
The cloud was the enabler. Snowflake realized, look, in the cloud, storage is effectively infinite. It's cheap, it's reliable, it's easily accessible via APIs. Compute, on the other hand, should be treated differently. It should be elastic, specialized, maybe even ephemeral.
Disposable almost. Use it when you need it, turn it off when you don't.
Exactly. This decoupling, that's the key. It unlocks tremendous elasticity and much, much better cost control. Storage just becomes this passive, secure, always-on repository.
Cheap and deep.
Right. And compute becomes pure processing power. You spin it up on demand, you size it for the specific task, and you scale it instantly if needed.
And critically, you scale them independently.
That's the beauty of it. Your data triples overnight. Okay, your storage costs go up a bit because cloud storage is cheap, but your compute costs don't change at all.
Until you actually run a query against that new data.
Precisely. Your costs track your actual usage much more closely.
Okay, so that separation leads to this idea of a multi-cluster shared data architecture. Can you break that down?
Sure, it sounds a bit technical, but the concept is straightforward and really important for understanding efficiency. Shared data means just that. There's only one central copy of your data.
One source of truth.
Yes, it lives in that independent storage layer we talked about. You're not making multiple copies of the data for different teams or different workloads. It's all there once.
Okay, and the multi-cluster part.
That's the compute side. This is where the magic happens. You can have multiple, completely independent compute clusters. Snowflake calls them virtual warehouses running simultaneously.
And they all access that same single copy of data in the storage layer.
Exactly. Think of it like a massive central library. The books are the data. And you can have dozens of separate reading rooms, the virtual warehouses, all using books from the main library at the same time.
And the readers in one room don't interfere with the readers in another room.
Perfect analogy. They are totally isolated. And that isolation is critical. It guarantees what we call workload isolation.
So back to our earlier example, the big ETL job and the sales dashboards.
In Snowflake, no problem. You run the ETL job on, say, a large dedicated virtual warehouse. You run the sales dashboards on a separate, maybe smaller, faster virtual warehouse.
And they don't slow each other down?
Not even slightly. They don't share compute resources. They might be hitting the same underlying data files, but the processing power is completely separate. One warehouse doesn't even know the other exists from a resource perspective.
That solves the resource contention problem completely.
It does. It's a massive architectural win that the old monolithic systems just couldn't deliver effectively. It really leans into the strengths of the cloud, that combination of cheap, abundant storage and elastic, pay-as-you-go compute. Snowflake just architected it smartly.
Okay, so that's the foundational principle, separation. Now, how do they actually build it? You mentioned 3 layers, right? The 3 layers. Separation is the big idea, the philosophy, but the implementation relies on these distinct components working together.
Exactly. They are distinct, but they're also very tightly integrated. You have the database storage layer at the bottom, the query processing layer in the middle, and the cloud services layer orchestrating everything from the top.
Let's peel them back one by one, starting at the foundation, the database storage layer.
Okay, so this is where all your data lands when you load it into Snowflake. It's the permanent home. It takes structured data, semi-structured data like JSON, Avro, Parquet. Basically, it's built to ingest pretty much anything.
But it doesn't just dump the files there, right? It does something smart with the data format.
Absolutely. As data comes in, Snowflake automatically converts it and stores it in its own proprietary, highly optimized columnar format.
Columnar, not row-based like traditional transactional databases.
Yeah.
Why is that important for analytics?
It's crucial for query speed. Think about a typical analytical query. You're often only interested in a few columns from a very wide table, maybe summing up sales figures or averaging prices.
Right. You don't need the customer's full address or their date of birth for that calculation.
Exactly. In a traditional row-based system, the database engine would have to read the entire row, including all those irrelevant columns, just to get the 1 or 2 values you need. That's incredibly wasteful in terms of disk I/O.
Okay.
With columnar storage, data for each column is stored together. So if you only need the sales amount column, the engine can go directly to the data blocks containing just that column's data.
It reads much less data from storage.
Orders of magnitude less data, potentially. This technique, sometimes called projection pushdown, dramatically speeds up those typical analytical queries.
Makes sense. Now, you also mentioned something called micro-partitioning. How does that fit in? These are potentially huge data sets.
Right. You need an efficient way to manage the physical data files. Micropartitions are Snowflake's answer. As data is loaded, Snowflake automatically breaks it down into smaller, immutable chunks. Think of them as manageable blocks of data, usually between 50 millibeads and 500 millibeads in size, compressed.
Immutable meaning they don't get changed once written.
Correct. If data is updated or deleted, Snowflake creates new micropartitions reflecting the changes, rather than modifying the old ones. This is important for things like time travel later on.
Okay, so you have these chunks. What makes them so smart?
The metadata. This is where layer 1 connects deeply with layer 3, the cloud services layer. For every single micropartition created, Snowflake automatically gathers and stores detailed metadata about the data within that partition.
What kind of metadata?
Critically, it stores the minimum and maximum values for each column within that specific micropartition. Sometimes these are called zone maps in the industry.
Min-max values for every column in every 500 millib chunk.
Yep. And this metadata lives centrally in the cloud services layer. Now imagine you run a query like where order date equals 2024-10-10.
Oh.
Before Snowflake even thinks about sending compute resources, a virtual warehouse, to read the actual data files, the cloud services layer checks this metadata, these zone maps.
Ah, see where this is going.
If the metadata for a particular micropartition shows that the minimum order date in that chunk is 2024-10-11 and the maximum is 2024-10-20, the optimizer knows instantly.
The data I'm looking for isn't in that entire 500 millib chunk. It could just skip it completely.
Exactly, without reading a single byte of the actual data file. This is called data pruning, and it's incredibly powerful. It allows Snowflake to ignore vast swaths of data, maybe 90%, 95%, even 99% or more for many queries.
Which is why queries can feel so fast, even on massive tables. It's not reading everything.
It's reading only the micropartitions that might contain relevant data based on the metadata. It's extremely efficient.
And security. What about encryption?
Non-negotiable and automatic. All data in the storage layer is always encrypted at rest. Snowflake manages this using strong encryption, like AES 256. It's not something you typically need to configure or worry about. It's just part of the service.
And one final point on storage. Snowflake manages this logical layer, but the actual physical bits sit on standard cloud storage, right?
Correct. When you set up Snowflake, you choose your cloud provider, AWS, Azure, or Google Cloud. Snowflake then provisions and manages the underlying S3 buckets, Azure Blob Storage containers, or Google Cloud Storage buckets for you.
So you benefit from the scale and durability of the major cloud provider storage infrastructure.
Exactly. Snowflake essentially adds its intelligent management and optimization layer on top of that commodity cloud storage. And importantly, you can't directly access these underlying files outside of Snowflake. You interact with the data only through SQL via the query processing layer.
Okay, that's a solid overview of the storage layer. Optimized, columnar, micro-partitioned, encrypted, and living on cloud blob storage. Now, let's move up the stack to layer 2. The query processing layer. This is where the action happens.
Yes, absolutely. If layer 1 is the highly organized pantry, layer 2, the query processing layer, is where you find the kitchens, the engines that actually do the work. This is where Snowflake runs your SQL queries, loads data, performs transformations. It's the compute engine.
And these engines are called virtual warehouses, or VWs. What exactly is a virtual warehouse?
Think of a VW as an independent cluster of compute resources. Under the hood, these are typically standard cloud virtual machines like EC2 instances on AWS or their equivalents on Azure or GCP that Snowflake provisions and manages for you.
A cluster specifically for running my queries.
Right. And a key architectural point is that these VWs are stateless. They don't hold any persistent data themselves.
So when a query runs,
When a query hits a VW, the VW reaches out to the storage layer, layer 1, pulls only the necessary micropartitions, identified by layer 3, the brains, performs the computations, the joins, aggregations, filtering, whatever the query requires in its memory and local cache, and then sends the results back to you.
and once the query is done, the data isn't lingering on the VW.
Nope. The VW might cache some recently used data for a short period to speed up subsequent queries, but it doesn't store it permanently. Its primary job is computation.
Now, how do you choose how much compute power you need? I've heard about t-shirt sizes.
Yeah, Snowflake simplifies this a lot. Instead of asking you to pick specific VM types or core counts, they use relative t-shirt sizes. X small, small, medium large, X large, 2X large, and so on.
Simple enough. Is there a logic to the sizing?
Yes, and it's important. It's geometric scaling. Each size up typically doubles the compute resources available in the cluster, and usually doubles the cost per second or per hour.
So a medium has double the power of a small, and a large has double the power of a medium.
Exactly. An X small might be 1 server node, a small 2 nodes, a medium 4, a large 8, and so on. This predictable scaling makes it really easy to understand the performance and cost implications of resizing.
And resizing is fast because of the decoupling.
Instantaneous, practically. Because the compute, the VW, is separate from the storage, Resizing a VW doesn't involve moving any persistent data around. Snowflake just needs to provision or deprovision compute nodes in the background and redirect the query workload.
That's huge. So if a query is running slow on a medium,
You can resize it to a large on the fly, often without even interrupting the query. It will seamlessly start using the additional resources. Or if you have a massive batch job,
like our ETL example.
right, maybe it takes 8 hours on a large VW. If you need it done faster, you could decide to run it on a 3x large, maybe finish it in just over an hour, pay more per hour but for fewer hours, and then immediately resize back down or suspend the warehouse.
That's incredible flexibility, true elasticity.
It really is. It lets you match compute power precisely to the workload's demands, moment by moment.
And this directly enables that workload isolation we talked about earlier.
Absolutely. Because each VW is an independent compute cluster, you can dedicate different VWs to different tasks or teams, and they won't interfere.
So one for data loading, one for the BI team's dashboards, one for the data scientist training models.
Exactly. You might put the critical BI dashboards on a medium VW that needs to be fast and responsive. The data science team might use a 2x large VW for a few hours a day for heavy model training. The ETL process might run on a large VW overnight.
And the data science training job, even if it's using tons of resources on its 2x large VW, won't impact the performance of the BI team's medium VW at all.
Correct. They are completely separate compute pools accessing the same shared data. It eliminates that resource contention problem.
Okay, let's talk cost efficiency again. How do VWs help there, beyond just right sizing?
Auto-suspend and auto-resume. This is another huge benefit of the architecture. A VW can be configured to automatically suspend itself after a certain period of inactivity, say 5 or 10 minutes.
Suspend meaning
Yeah.
it shuts down.
Essentially, yes. It stops the underlying compute instances, and crucially, Snowflake stops billing you for compute credits for that warehouse while it's suspended.
So you only pay when it's actually running queries.
Pretty much. Then, as soon as a new query is submitted to that suspended warehouse, it automatically resumes, wakes up the compute resources typically in just a few seconds, and starts processing the query.
That's a massive potential cost saving compared to leaving traditional servers or VMs running 24/7.
It is. But, and this is an important but we should touch on, that incredible flexibility also introduces a need for governance.
The potential downside, the double-edged sword.
Exactly. It's fantastic that you can spin up a 4x large warehouse instantly. But if someone on your team does that, runs a quick test, and then forgets to suspend it or doesn't have auto-suspend set correctly,
You need our
his
team's
plan and a 4x large meter runs fast. Very fast. Hundreds of dollars per hour, potentially. So, while the architecture enables cost efficiency, realizing those savings depends on good practices. You need proper monitoring, maybe setting spending limits, using resource monitors.
Which is a function of the next layer we'll talk about, I assume.
Yes, the cloud services layer handles governance features, but the point is the responsibility shifts. It's less about tuning infrastructure for cost and more about managing usage for cost.
So the conversation changes from, can we even run this,
Mm-hmm.
to, okay, how fast do you need this to run, and what's the cost per second we're comfortable with for that speed?
Precisely. It's a different way of thinking about resource allocation, enabled entirely by this decoupled compute layer.
Okay, we've got the optimized pantry, storage layer, and the flexible kitchens, query processing layer. Now for layer 3, the cloud services layer. You called this the brain, the control center.
Yeah, that's a good way to think about it. This layer is like the central nervous system or the management hub for the entire Snowflake platform. It coordinates everything happening in the other 2 layers.
And unlike the virtual warehouses, which use compute we pay for directly via warehouse credits, this layer runs on compute managed entirely by Snowflake.
That's right. It's part of the overall Snowflake service. You don't provision or size resources for the cloud services layer directly. Snowflake handles its scaling and availability behind the scenes.
And its job list is pretty long, right? It does a lot more than people might realize.
Oh, absolutely. It's the unsung hero in many ways. Its responsibilities are critical for making Snowflake feel like a seamless, integrated platform rather than just separate storage and compute components.
Let's break down some of those key responsibilities. Where should we start? Security.
Good place. Authentication and access control. When you log in, when you run a query, it's the cloud services layer that verifies who you are, checks your role, checks what permissions you have, which databases, tables, and even which virtual warehouses you're allowed to use.
So it enforces all the security policies.
Correct. It ensures data governance and prevents unauthorized access across the entire platform.
Okay, what's next? You mentioned metadata earlier being crucial.
Hugely crucial. Metadata management is arguably one of the most important functions of this layer. It maintains the central catalog of everything.
Everything meaning.
Table definitions, schemas, view definitions, the data types of columns, but also, crucially, the information about the physical storage, where each micropartition lives in the underlying cloud storage.
And those zone maps we talked about.
Yeah.
The min-max values.
Yes. All that statistical information about the data within the micropartitions is stored and managed here. And it also tracks the transactional history of the data, which micropartitions were valid at which points in time.
And that history tracking is what enables those magic features like time travel and cloning.
Exactly. Without the cloud services layer meticulously tracking the state and history of every micropartition via its metadata, features like zero-copy cloning and time travel simply wouldn't be possible. It's the system's memory.
Got it. What else is on the cloud services checklist? Optimization.
Query optimization, yes. This is huge. When you submit a SQL query, it doesn't just go straight to a virtual warehouse.
It gets intercepted by layer 3 first.
Yes. The cloud services layer analyzes the query, looks at the metadata, including those zone maps, and figures out the most efficient way to execute it.
Like deciding which micropartitions it can prune or skip.
Precisely. And also determining the best join strategy if you're querying multiple tables, how to distribute the work effectively across the nodes within the chosen virtual warehouse, and so on.
And this happens automatically. We don't need to provide hints or manually tune indexes like in the old days.
Largely, no. That's one of the biggest operational reliefs Snowflake provides. The optimizer handles the heavy lifting of planning the query execution, leveraging the rich metadata it maintains. It's constantly getting smarter, too, as Snowflake updates the platform.
Okay, so security, metadata, optimization, what else? Managing the resources themselves.
Resource management, definitely. This layer keeps track of all the virtual warehouses. It handles the provisioning when you create or resize one. It manages the auto-suspend and auto-resume logic based on your settings.
It's the traffic cop for the compute layer.
Kind of, yeah. It ensures resources are available when needed and turned off when idle to save costs. And related to that is transaction management.
ACID properties,
You can.
making sure things stay consistent.
Exactly. Especially in a system like this, where you have potentially many independent compute clusters, VWs, reading from and writing to the same shared data layer, you need a strong coordinator to ensure everything stays reliable and consistent.
Can we quickly recap ACID in this context?
Sure.
A is for atomicity.
Right. Transactions are all or nothing. An UP date affecting 1,000,000 rows either fully completes, or if it fails halfway, it rolls back completely, leaving the data as it was before. No partial changes.
C for consistency.
The database always moves from one valid state to another. It enforces constraints and rules, so you don't end up with logically corrupt data.
I for isolation. This seems really important with multiple VWs.
Critical. It ensures that concurrent transactions don't interfere with each other. If one VW is inserting data while another is reading, the reading query sees a consistent snapshot either before the insert started or after it's fully committed, not some weird half-done state.
Yeah.
This is vital for concurrency.
And D for durability.
Once a transaction is successfully committed, the changes are permanent. They'll survive subsequent system crashes or restarts because they're safely written to the persistent storage layer, layer 1.
And the cloud services layer is the guarantor for all of this.
It orchestrates it. It manages the transaction boundaries, ensures isolation between VWs, coordinates the commit process with the storage layer. It provides that rock-solid, reliable database foundation despite the distributed nature of the compute.
Wow, okay, so layer 3 is doing a ton of work behind the scenes. Security, metadata, optimization, resource management, transaction control.
It really is the glue and the intelligence that makes the whole decoupled architecture work seamlessly as a single service. It abstracts away enormous complexity from the user.
Which leads us nicely into the user experience.
Yeah.
How does this architecture translate into tangible benefits? Right, we've dug into the layers, the nuts and bolts. But why should someone listening, maybe an analyst or a data engineer, really care about this architecture? What does it do for them? Hashtag tag 3.1, performance, concurrency, and scaling.
Well, the first and most obvious benefit is the combination of performance, concurrency, and scaling. It addresses the core pains of the old systems.
We touched on instant elasticity. That ability to resize compute almost instantly,
Yeah.
that's a direct result of decoupling, right?
Absolutely. If your query is slow, you're not stuck. You're not filing a ticket for a DBA to spend days tuning indexes. You just resize the warehouse.
Right, medium instead of a small. Or large instead of a medium.
Yeah, it might take 30 seconds, you get more compute power immediately, the query finishes faster, and then you can scale back down or let it auto-suspend. That ability to react instantly to performance needs is transformative.
It changes the whole dynamic around performance tuning.
It really does. And think about those peak load times, like month-end reporting. Instead of everyone suffering on a slow system.
You just temporarily beef up the reporting VW.
Exactly. Throw more compute at it for those few critical hours or days. Pay for the extra power only when you need it, get the reports done quickly, and then scale back. Predictable performance even under heavy load.
Which ties back to workload isolation, too. High concurrency without the pain.
Right. In the old shared systems, if hundreds of users hit the dashboards at 9 a.m. Monday morning, performance often degraded for everyone. With Snowflake, you can isolate those workloads.
Give the critical dashboards their own dedicated VW.
Precisely. Maybe the customer-facing app gets its own always-on, appropriately sized VW for guaranteed low latency. Internal analysts use another. Data loaders use a third. They don't steal resources from each other.
So you can actually offer different service level agreements, SLAs, for different user groups or applications reliably.
Yes, because their performance is determined by the dedicated resources you allocate to their VW, not by what other unpredictable jobs might be running on the system at the same time. That predictability is huge. Hashtag TagTech 3.2, data management features, the aha moments.
Okay, performance and scaling are clear wins, but the architecture also enables some features that feel, well, almost like magic, especially coming from older systems. These rely heavily on that clever metadata management in Layer 3, right?
Definitely. These are often the aha moments for new users. Let's start with zero-copy cloning.
This one sounds cool. Zero copy.
It is cool and incredibly useful. Think about needing a copy of your production database for development or testing. In the past, if your database was terabytes or petabytes,
that was a nightmare. You'd wait days or weeks for a physical copy to be made. It would consume massive amounts of expensive storage.
Exactly. A huge pain point slowing down development cycles. Zero-copy cloning in Snowflake lets you create a full, independent, writable clone of a database, a schema, or even just a single table.
Instantly, regardless of size.
Instantly, because it's not actually copying the petabytes of data.
How does it work then? The metadata trick again?
It's all metadata. When you issue the clone command, the cloud services layer simply creates a new set of metadata pointers that reference the same underlying physical micropartitions in the storage layer that the original object uses.
So the clone points to the original data blocks initially.
Right. Your clone is ready in seconds, and it looks and feels like a complete copy. Now, the key is it's writable. If you then update or delete data in your clone...
What happens? Does it change the original?
No, that's the beauty. Snowflake just creates new micropartitions to store the changed data for the clone only. The original micropartitions remain untouched, still serving the production object. The clone's metadata gets updated to point to the new block for the modified data, while still pointing to the original blocks for unchanged data.
So you only pay storage for the changes you make in the clone, not for the entire cloned data set.
Exactly. It's incredibly efficient for storage. And the impact on workflows is massive. Dev and test environments spun up in seconds with production data. Staging environments created instantly. It dramatically speeds up development and reduces infrastructure costs.
Okay, that is an aha moment. What's the other one? Time travel.
Time travel. Another feature directly enabled by the architecture, specifically the immutable micropartitions and the historical metadata tracking in Layer 3.
So this is like an undo button for your data.
Pretty much. It allows you to query data as it existed at a specific point in the past, within a configurable retention window.
How far back can you go?
By default, it's usually 24 hours, but you can configure it for standard accounts up to 90 days for enterprise editions.
And how does it work? When data changes, Snowflake doesn't overwrite.
Correct. Because micropartitions are immutable, when you update or delete data, Snowflake keeps the old micropartitions for the duration of the time travel window and creates new ones for the current state. The cloud services layer's metadata tracks which partitions were valid at which timestamps.
So if I accidentally run a delete statement without a where clause at 10:05 a.m., panic.
Less panic than before, you could simply run a query like select from my available the T, Timestamp, Harwell 2024, 10-10, 10 Snowflake uses the metadata to find the micropartitions that represented the table's state before your mistake.
Or you can use undrop table if you drop the whole thing.
Exactly. There are commands to easily restore tables or schemas based on that history. It turns data recovery from potentially a major backup restore operation taking hours or days
into a self-service SQL command that runs in seconds or minutes.
It's a huge safety net and operational advantage. Hashtag TechChack 3.3. Simplicity and maintenance.
Okay. Performance, cloning, time travel. These are powerful. It feels like the culmination of all this is simplicity, making life easier for the data teams.
That's absolutely a core benefit. The architecture is designed to abstract away a massive amount of traditional operational burden. Think about all the things DBAs used to spend their time on.
Like managing storage, planning capacity, installing patches, upgrading hardware, performance tuning like indexing and partitioning.
All of that. In Snowflake, most of that complexity is handled by the platform, primarily by the cloud services layer. You don't manage physical servers or storage arrays. Updates and patches are applied automatically by Snowflake.
And performance tuning is largely automated by the optimizer.
Right. You don't typically need to create indexes or manually partition data for performance. The micro-partitioning and metadata handle a lot of that optimization automatically. High availability, data replication for resilience that's built in too.
So the data engineering team, the platform team, they can focus more on building data pipelines, creating data models, delivering analytics.
Exactly. Less time spent keeping the lights on, more time spent delivering actual value from the data. That shift in focus is incredibly valuable for most organizations.
And those automatic features we mentioned, auto-scaling based on load with multi-cluster warehouses, auto-suspend for cost savings, they reinforce that simplicity.
They do. It's designed to be more hands-off from an infrastructure management perspective. The goal is a platform that largely takes care of itself, allowing you to focus on the data, not the plumbing.
It fundamentally changes the job, moving it up the value chain.
Absolutely. From infrastructure caretakers to strategic data enablers. That's the promise of this kind of cloud-native architecture.
Okay, let's try and synthesize this. We've gone through the layers, the features, the benefits. What's the big takeaway here?
So I think the main point is that Snowflake isn't just an evolution. It's really a paradigm shift from those older, tightly coupled systems. It fully embraced cloud principles.
Elasticity, separating storage and compute.
Right. It moved to this flexible, consumption-based model where you pay for what you use when you use it. And that entire shift, that entire platform capability, is fundamentally enabled by its specific three-tiered architecture.
The decoupling of the storage layer from the query processing layer, all orchestrated by that intelligent cloud services layer.
Exactly. That structure is what allows it to tackle the modern data challenges, massive scale and high concurrency, in a way that legacy architectures just couldn't.
So understanding this architecture isn't just academic. It's pretty critical for anyone working in data strategy today.
I'd say so. If you're building data products or pipelines, knowing how the underlying platform scales, how it handles concurrency, how it manages cost, that influences how you design things.
Right. Now, we touched on cost governance earlier. That separation of compute and storage, the pay-per-second billing for compute, it really forces a different way of thinking about project costs, doesn't it?
It absolutely does. And this leads to a really interesting final thought for people to consider. What's fascinating is how this architectural separation, this granularity of cost, might change how businesses approach data projects fundamentally.
How so?
Well, think about it. In the old world, trying something new often meant a big upfront investment in hardware or software licenses, long planning cycles, high-risk, slow iteration.
Right. The barrier to experimentation was high.
Very high. But now, if spinning up a powerful warehouse for an hour to test a complex data science model costs, say, $20 in compute credits,
The cost of failure, or just the cost of trying something new, is drastically lower.
exactly. The low barrier to entry and the instant scalability encourage experimentation. It shifts the financial model from slow, heavy capital expenditure, CapEx, to a much more flexible, iterative operational expenditure, OpEx model for data initiatives.
So the architecture doesn't just change performance. It can change the business's risk tolerance and speed of innovation around data.
That's the provocative question, I think. When compute costs are so transparent and elastic, completely separate from storage costs, how does that change your budgeting? How does it change which data projects get prioritized? Does it make you bolder, faster?
That's definitely something to mull over. How does architectural agility
Yeah,
translate into business agility?
precisely.
Fantastic. Well, that's been a really insightful deep dive into the architecture that's powering so much of the modern data world. Thanks for breaking that down.
My pleasure. It's a fascinating piece of engineering.
And thank you for joining us on the deep dive.